Hello, ladies and gentlemen. This is IKX Talks. Every Friday we met on the line. So we use a technique to connect the world and the universe. So this is a great honor for me to host this session instead of my colleague Jack Dish. He already hosted 2 or 3 sessions and gave several talks today. So he is getting tired. So I'm going to, do his job. So it's Alice from Peking University. Actually, ICANX is one of my favorite and initiative. So it is my great honor, to do all these sessions. And today, and at the very beginning, I want to announce 2 news we're going to have. First is we will have ICANX Young Scientist Award. Actually, this will be honor on ICANX stage for the young scientists. So the deadline for this application is next month. So the people who get his PhD, in 10 years will be, accept qualified to apply this award or be nominated by others. So you should provide 5 materials. And for the evaluation process, we are first, based on paperwork, and then we have the defense part in ICANX platform. So that's a committee and the prize. The winner of this Young Scientist Award will get an award to $500 and also get a chance to deliver a talk on ICANX next year. And we will have the ICANX Summit this year in Hainan Island. It was December 19 to 21. So everyone enjoy ICANX. You are welcome to join our ICANX Summit to meet all the speakers and all the leading scientists in the world. So after these 2 announcements, now come to our ICANX talks. Actually, in September, everyone knows that we have 4 speakers. And first week we have John Rogers, then we have Professor Isach, and last week we have Professor Nitish. And this week we have Professor Xi Peng. Is my colleague in Peking University, and today we have a big, very outstanding panelist. We have Da Yong from University of Technology, Sydney. We have Ming Hui, also from Singapore. We have Guo Chen, our challenger, was from Chile too. So without further ado, let's welcome our speaker, Professor Xi Peng. Let me first give a brief introduction of Professor Xi Peng. Actually, if you are luckily to hear yesterday his interview, you all know that Professor Xi Peng was a very interesting person and one of the most creative person. I think he was working in the super resolution field for more than 10 years or 15 years, and he traveled around the world and to get collaborate with different peoples and also developing a lot of high technologies and doing many breakthroughs. Also, several achievements was ranking #1 in the world. Right, he won a lot of honors and a lot of prize and get many titles. So if I go to read the list of his titles, maybe we don't have time to listen to his talk. So yeah, so let's welcome Professor Xi Peng to tell us your adventure in super resolution, please.
Thank you, Alice, for your kind invitation and a nice introduction. It's my really great honor to be a speaker in the ICANX talks. My name is Peng Xi. I'm from the College of Future Technology in Peking University, and I'm also jointly affiliated with the College of Engineering in Southern University of Science and Technology. And the title of my talk is Super Resolution Microscopy and the Adventure on a New Dimension. So as we all know, optical microscope provides in vivo and non-invasive modalities, facilitating us to see through the live cells. And because optical microscope is highly welcomed in the biological community, we can arguably state that the resolution of optical microscope sets the standard for the depth of biological research. But we also know that any microscope, especially optical microscope, has a definite resolution limit. So what is the resolution? If we see the diffraction limit, we will find that this resolution is around 200 nanometers or half lambda. And if we see, which means if you're going deep into the specimen, and you will not be able to resolve anything smaller than 200 nanometers. Yet, if you look into the cell, you will find that the organelles features with size typically several tens of nanometers. That means we cannot see them clearly. So the driving force pushes the technology to going beyond the resolution limit, and a series of novel techniques aiming at breaking this resolution barrier has been invented, and they were awarded the Nobel Prize in Chemistry in 2014. And the awardee, the laureates were Eric Basic, Stephen Hill, and Professor William Molnar. So before we go into the regime of super resolution, let's look back at what limits us, what is the resolution barrier. So we all say that a point subject converts to a point image. So by using a lens. If this point-to-point conversion is true, let me ask you one question. What's the size of a point? You may say that it's 1 micron. I can instantly say, okay, let's go to 1/10 of that 0.1 micron. And we can go in smaller, smaller, smaller until it shrinks to a dot, which is dimensionless, which has the size of 0, and it is a delta function. But this point, if you convert it by an optical microscope system, it will not being able to be reconverted into an ideal point. Instead, it becomes a point spread function, which is what we're familiar with, the airy disk. And this airy disk, the diameter, the size of this point spread function determines the resolution. So if you, those of you who wear glasses, if you remove your glass, you will see this world being blurred. And each point actually, which is because your point spread function is expanded. So speaking of the resolution, we know that if your PSF is very wide, when 2 emitters are getting too close and emit simultaneously, they cannot be resolved. This is the whole point of resolution. So let me ask you, how can you get super resolution? With that, if you go to this sentence, you will find that there are 2 conditions. If the point spread function is very wide, or 2 emitters getting close by emit simultaneously. So if we break any one of them, we will be able to generate super resolution. For example, for the first one, we initially said the point spread function is very wide. How can we narrow it down? We can use a scheme called stimulated emission to effectively deplete or erase this excitation fluorescence. So if we can effectively erase the peripheral of this PSF, the residual effective PSF is getting narrowed down, and we get better resolution instantly. And you will find that since this is a game of erasing, we can increase the power for this erasing beam or this steady beam and get better and better resolution, which can be documented nicely with this equation. So next, if we break the second condition, when 2 emitters getting too close, they will never emit simultaneously. So this work is being done jointly by Professor Eric Basic and Professor William Molnar. So let's say we have 5 molecules that were close by and emitting. and simultaneously. So if you watch them, you will find the sum of their PSF. You cannot easily distinguish them. But if we only allow any one of them to emit light, we are not resolving 2 or 3 of them. We're localizing each molecules, and we can accurately find their position. And after 5 iterations, we will be able to find the precise locations of these 5 molecules. And for a complicated biological cell specimen, we can do multiple iterations to get their locations. This is termed single molecule localization microscopy. So let's go to the first part, which is STED. We find that although theoretically increasing I, we can improve the STED resolution. However, the fragileness of biological specimen prohibits us to further increase this erasing beam laser power. So our first question is, we ask ourselves, can we improve the STED axial resolution by 6-fold, lateral resolution further by 2-fold, and signal by twice, but without increasing any laser power? Because if you increase the laser power, these tasks were easy. However, it breaks the fluorophore, it damages the cell. So how can we do that without increasing laser power? This work is abbreviated MEANS, which means mirror enhanced axial narrowing super resolution microscopy, is done by my students Xisan Yang and Hao Xie, and also Dr. Eric Alonas in Georgia Tech. So I believe before joining this seminar, most of you has going to use an optical device called mirror. Mirror is such a device that we use almost every day, and the data has shown that female use much more frequently than male. And it creates a virtual image for us, a perfect virtual image. So, and we also know that there is a technique called TIRF, total internal reflection fluorescence. So for those of you who do not know total internal reflection, you know that this signal, the reason that you can see me is because the signal is broadcasted through optical fiber, and the total internal reflection is a key component for the fiber transmission because it maintains the signal within the fiber core. So how does that happen? If you your incident comes from a high refractive index to a low refractive index, if you after the critical angle, you have this evanescent wave only, which means it propagates very shallowly. It's like roughly 100 nanometer. So if you put fluorophores on top of that, you will see the fluorescence image, which converts the evanescent wave into propagating wave. Comparing wide field with TIRF, you will find that TIRF is not a super resolution technique. However, because it narrows down the axial from several 100 nanometers into 100 nanometers, you will see a sharp contrast image, high with high SNR. And there is another technique called 4-pi microscopy. So previously, for those of you who did confocal microscope, you know that the confocal's axial resolution is much worse than the lateral resolution. So representing by a point spread function, the worst resolution means an elongated PSF, which is like a piece of rice. So if you see this rice, you will find that its length is around 600 to 700 nanometers. However, if we create a phenomena to allow them to interfere with each other, we can narrow down this PSF from 700 nanometer down to 100 nanometer, which means a 6 to 7-fold of axial resolution can be obtained by this interference. And in reality, if you put two objectives opposing each other, you will generate such interference and create this 4-pi point spread function. This is a very nice setup, and it has been commercialized by Leica, but because it is very complicated, meaning you have to ideally overlap these two, the point spread functions of objective 1 and objective 2. So it makes it hardly accessible nowadays. So when we think about that, we think maybe we can change this game by changing the objective 2 and the subsequent cover glass with a piece of mirror. So if we have a mirror, then we can really image the top part into the objective 1 into objective 2. So literally, I did this. We grow cells on top of a mirror and put a piece of cover slip onto it. And we put it on top of an inverted microscope. So as I explained, for turf microscopy, it appears on the layer of cover glass. But when you have confocal modality, your PSF getting closer and closer to this silver mirror, what you see is a semi 4 pi configuration, and then you have another layer of image. So for turf, I collect this image, and for means, we get this image. And when we merge this image with side color, you will realize that they reflect different layers of information, which if you collect only a wide field image, you get both of them, but you cannot distinguish which layer belongs to which. So we have also studied the point spread function of this confocal 4 pi and means. Initially, I assumed that means would have the same PSF as 4 pi. But because of the half-wave loss, we find that this PSF actually floats above the mirror for around 100 nanometers, and the PSF's width is around 110 nanometers. And if you look at the intensity, you will find that because of the constructive interference, they have provided us a 3.6 folds of intensity increase, which significantly enhances the local field for means, which means we can get instantly six-fold of axial narrowing plus twice of spatial resolution enhancement without increase of any laser power. So we have, to demonstrate this, we have imaged the inner rings for a nuclear pore complex. Because it's termed a nuclear pore, it must look like pores, and it is verified by electron microscope and that it's indeed pores. But under a conventional standard microscope, due to the limited resolution, we cannot see the porous structure. And guess what? When we put this specimen beneath our means state microscope, we see a series of porous structures being revealed, benefited from the high resolution that we can provide at a very low laser power. And this work was reported by laser light science and applications, and it is instantly highlighted by Nature Photonics. And it's also being covered by a series of media. And next, I'm going to talk about ultra high spatial resolution mitochondrial imaging with STED. This work is done by Dr. Xisan Yang and Zhaoyang Wu in my group, and in collaboration with Dr. Zhigang Yang in Shenzhen University. So mitochondria, it is the cell's power plant. It provides power for the cells. And the term mitochondria actually is a combination of two Greek words. Mito means line, chondria means grain. So it has naturally two different types of forms. And interestingly, these mitochondria carry their own unique mitochondrial DNA. It is a subcellular organelle, means it's a part of our cell, but it carries its own DNA. So imagine this. So there are a lot of stories or hypotheses about the origin of mitochondria and why mitochondria has its own DNA. So one of them is that mitochondria is arising from an exogenous bacteria entering the cell and co-host by the cell. So if you play games, you probably know that at Sony PlayStation, there is a famous game called Parasite Eve 2. So it is about the story of mitochondria in the human body. It wakes up and attacks us in turn. And it tries to control its host. So within this mitochondria, actually, we can see a lot of fusion and division of mitochondria cristae. And because SIM can only provide spatial resolution of about 100 nanometers, it is insufficient to reveal these complicated cristae structures. And for the temporal resolution of single molecule localization, as I explained before, the single molecule localization is relatively slow. So it has insufficient temporal resolution to see the complicated cristae dynamics. So making the state seems to be the only choice for studying the mitochondria's time-lapse dynamics. However, there is one thing. Mitochondria are very sensitive to light, which means they are phototoxicity. If you give too much of high intensity, then it breaks and it converts to be from mitochondria, and it becomes very unhealthy and it breaks down. So make it very hard, very difficult to study it. So in collaboration with Zhigang Yang and Professor Jinle Qu at Shenzhen University, we have developed this so-called MitoESQ 635 dye. It is an it demonstrates high photostability, and it is a wash-free dye, and it demonstrates very high cell compatibility. So we can image it very long time without any photo damage. So if you're comparing with the famous Mitochecker, which is a standard for mitochondrial imaging, you will find that Mitochecker on the 50s, it's damaged already like half, and then from on 100, there is literally very few dye can resist the phototoxicity. However, for MitoESQ 635, we can image up to 300 without much loss on the signal. And we have seen from the joint tagging with Mitochecker and this MitoESQ, we find that they colocalize very well with a high R value, and makes it and presents the same performance as the gold standard. And we have acquired a series of mitochondrial images, and we compare it with scanning electron microscopy. So from the literature, we see very rich dynamics for different types of mitochondria. And as you can see, our optical microscope, because it provides super resolution, it can gives you ultra detail for this mitochondria. However, if you the more benefit for using optical super resolution is that we can provide dynamics, studying the fusion and the fission process, which is not available for the SEM counterparts. And because our technique is so powerful, we can even image a 3D stack. So from the bottom to the top of this cell, and we can find the distribution of this mitochondria in a 3D cell. And we have imaged actually up to an hour for steady super resolution image with exposure for 4 seconds and dark recovery for 71 seconds. And we achieved a resolution of 35.2 nanometers with only a steady power of 9 milliwatts, and we can see clearly the fission process of this from this movie. And we also see fusion. If you look into this part of the movie, they were initially two parts, and then they joined with each other. And from another movie, you see that it forms this hollow bubbles from this metal to they merge, and they're forming these hollow structures, and the crystal of this mitochondria can be clearly revealed. And the third part is about polarization theme, which is the abbreviation of structured illumination microscopy. This work is jointly done by Dr. Kao-Zhang Hao and Meiqi Li, which is a PhD candidate in my group, and also Dr. Xinye Chen in Tsinghua University. So I believe for the Chinese audience, all of you have went to the cinema to watch the Wandering Earth, the famous movie in 2019. And for those of you who has not watched this movie yet, I strongly encourage you to go to the cinema or go to the website to watch this this great sci-fi movie. And the author for this is Liu Cixin, and his famous sci-fi is the three-body problem. And in this three-body problem, he mentioned a dimensionality reduction strike, 降维打击. What is dimensionality reduction strike? So imagine I learned Kung Fu like Li Xiulong. I can practice Kung Fu. So if going offline, I may hurt you with my Kung Fu if you are my enemy. But because I'm online now, in reality, I'm on 3D plus time domain, so it's like 4D. So if you do give me a dimensionality reduction, I can only go to becomes from offline to online like this. So no matter how hard my Chinese Kung Fu is, I cannot hurt you, right? And if you give a further dimensionality reduction, my voice or I can be freezed into a picture, and then you cannot further you cannot see my move, and that is the power for dimensionality. So if you go to the dimension, I would like to point you to this famous paper, which has led to the Nobel Prize for arithmetic. So what is this paper? It is a paper published in 1995 on optics letters, and it is a pure theoretical paper. And the title for this paper is Proposed Method for Molecular Optical Imaging. Let's see what Eric proposed. So he says, if we have a bunch of molecules, they emit light, and if we have an optical lens, which is an low pass filter with a large point spread function, what we see is that they were highly blurred, and you see a bunch of those molecules. You cannot distinguish their position precisely. But if you introduce another dimension to them, for example, if you from this 2D, if you put it into this, if you imagine each point is like a pin with a big pin head and a very narrow pin, then you can install this pin into different heightness, and all in a sudden their position can be uniquely distinguished. And on this piece of paper, you record all the molecules' position. And naturally, we know that later on, what Eric did is that he introduced the time domain, temporal dimension into this problem. So let's see, if I have two molecules, my two fists are two molecules, you cannot see them because they were close by. But if you introduce a dimension to me, making me rotate, and you will see that they were separated far apart with each other. So this is a power for a new dimension. And instead, if we go back to STED, we will find that, okay, the central part is generating spontaneous emission, while the peripheral is generating stimulated emission, which means another color. And we are doing a spectral dimension separation between these two molecules. And when we realize that it's a game about dimension, you will suddenly find out that, okay, super resolution microscopy, there is nothing really beyond conventional physics. It obeys all the laws of conventional physics, but how do they surpass the diffraction limit? It can actually separate molecules. It introduced distances from a new dimension, making them far away, and then you can separate them. Okay, it's a game about dimension. I and Professor Dang Jin has collaborated toward the application of upconversion nanoparticles instead. And we find that there is a rich library for upconversion nanoparticles, and we use the spectral dimension as a weapon to decrease significantly the power acquired for STED. I don't have further time to introduce this part, but if you can also imagine that the temporal dimension and the spectral dimension, they can sum up together to generate a better time-gated STED. And being a physicist, we are looking for a new dimension that is yet to be fully revealed by this super resolution, and which can be further employed. So we find that these fluorophore actually, they are dipoles, meaning when you see an subcellular organelle, typically they don't emit light. So what you do is you either tag a fluorophore molecule, or you gene transfer, gene editing, and making the fluorescence protein embedded into this organelle. So when you see this fluorophore, you will realize that what you're actually looking is the underlying subcellular organelle. So if we can tell the direction of this fluorophore, we can naturally give you a further information about the direction of this subcellular organelle, right? So this is the whole point for the dipole, and the dipole can be excited by a linear polarization in maximum, and if you excite it with perpendicular polarization, it gives you zero intensity for the fluorescence emission. So there's another technique which I haven't described yet, which is called structure illumination microscopy. And this structure illumination microscopy can be best interpreted by this Mori pattern. So if you go far away from your screen, or if you move your glasses, you will find that you will not be able to see these fine patterns in image B, but you can see these stripes, these black stripes in the figure C. So why is that? This pattern in figure C is actually the low frequency component from the overlapping of A and B. And let me give you an example. So here I have a transparent slides, and here I have a grating or a structured feature. So if you look at them, you cannot see the structure, but if you overlap them, you will find that from the rotating of this angle, you will be able to see those Mori patterns clearer and clearer when they appear, right? And when I fully rotate them to the same angle, you will see airy these characters this sentence clearly. So let me rotate them again. You'll see the Mori patterns. So this experiment gives us an information that we can convert the high frequency, which means the ultra fine structure. We can convert them we can move them into the low frequency and make us being able to visualize it using a microscope. So if we illuminate the specimen with an structured illumination generated by this Young's double slit, and we will see the stripes, and we will be able to generate 3 copies of these components. And when we combine all the 3 components in 3 different directions, we will have an expanded optical transfer function. And by further transfer it from the Fourier domain into the spatial domain using an image processing technique, we will be able to generate figure GH out of the original figure AB. You can see that the power of this SIM, it generates twice of resolution enhancement, but the ultra structure it provides is very rich. And in structured illumination, we give an sinusoidal in spatial domain. And in order to generate a highly efficient sinusoidal interference, we need a polarized light matching the direction of this spatial sine curve. And previously, I've described that if you want to determine the angle of each dipole, you need to rotate your excitation. And the dipole's response is also sinusoidal. So this triggers us to think, it seems that these two has a lot of similarities. Can we put them together to collect both the information, spatial structure, super resolution information, as well as the dipole orientation information from the original SIM data? And the answer is yes. So before giving you how we did that, let me show you some of the pictures. So this is the wide field image of an microtubule. SIM undoubtedly gives you twice resolution, make the image crystally clear. However, if you go further, resolve this microtubules with our polarized SIM, you will appreciate that we give the GFP's direction of each molecules. And if you look closely, you will find that for this one, its direction is like this. And for this one, its direction is like this. It's always perpendicular to its propagation for this microtubules growth. So it's very striking for us. And in collaboration with Professor Qinghai Dai's group in Tsinghua University, we successfully converted this mathematical problem by expanding it into both X, Y, and alpha direction. So in alpha, we know that it's a modulation from -½ pi to ½ pi. And it's repeated itself, making it a natural structure illumination in orientation dimension. And by using the same principle for resolving the ultra structure in SIM, we successfully expanded the data further in polarization domain, making the PSIM not only has the ultra structure or super resolution in terms of the X and Y direction, but also containing the dipole orientation information. So further, through collaboration with Professor Xiaowei Chen in the College of Future Technology in Peking University, we studied the microtubules evolution for into OS cells, and you can see from this nice movie. And you probably have seen this movie as well, which is actin floating the myosin walking along the actin, which is like an acrobat walking along the rope. So here, what we do is we flip the acrobat down and see how it steps this rope. And this is in collaboration with Professor Xiangdong Li in the Institute of Zoology in CIS. And we find that you can see there are long elongated actins, and their direction is along their propagation. And there are also very, very short actin filaments, and they walk toward different directions driven by the myosin when you provide sufficient ATP to it. And we have tracked the moving direction and the dipole orientation. We find that they were correlated very well. And even for those tiny actins, we can report its angle precisely, taking the advantage of the dipole resolving power for polar sim. And when you don't have sufficient ATP in it, the actin starts to wobbling instead of floating and drifting. And next, you probably know that aside from the besides from the Nobel Prize, Professor Xiao Weizhuang also won the Breakthrough Prize in 2019 for her distinguished work on optical fluorescence super resolution microscopy. So one of her work is the successful result of the relationship of actin spectrum and the other proteins like adenosine. So we know that actin can be dissected into small parts by adenosine, and from the dual color storm, we find that they were periodically arranged. So Professor Zhuang given a hypothesis diagram that the spectrum links the actin, and the actin links like rings. So end to end, forming an end-to-end structure. So is that really this way? In collaboration with Professor Yan Zhang in the IDG McGovern Brain Science Institute, we have further studied the MPS structure of this axon. So we find that inside the neuron cell dendrites, there were also the actin were in perpendicular with their propagation angles like this. So if this hypothesis is true, the actin forming rings like this, it must containing this bluish or greenish color in here. Yet what the color what we see or the orientation what we see is, instead of being like this, it's like this, making us rethink what could be the other possibility for actin to forming such kind of rings. We presented a side-by-side hypothesis, which explains why actin adenosine being look like this. And this neuronal structure, because our polarization theme provides you better angular or orientational information, we can see the side-by-side arrangements for this actin spectrum organization. And we also benefited from the super resolution capability of SIM. We see that there were also nicely periodic with a period of 184 nanometers. So this paper was published on Nature Communications in December 2019, and it's been highlighted by Nature Methods, demonstrating our method were compatible for 2D, 3D turf theme, and also revealed the side-by-side actin ring structure. And last but not least, let me talk about the spectrum and polarization optical tomography work. This work is done jointly by Kao Zhanghao, Meiqi Li, and Wenhui Liu in collaboration with Professor Da Yongjin in UTS and the South Tech. So if we go to the cell anatomy, we will find that there are multiple subcellular organelles. Cell itself is a very rich world. And previously, when we try to study the organelles, we label each of the organelles by using one fluorophore or one color. So for example, for this picture, the blue is the nuclei, the green is the microtubule, and the red is the actin. Why we seldom see more colors? If you look at the spectrum of an fluorescence, you will find that within this visible spectrum from 400 to 700 nanometers, each fluorescence emission spectrum has typically a width of over 50 nanometers, which means they heavily overlap with each other, making it very difficult to choose several more fluorophores, but not overlap, but without any overlap. So this heavily overlap, they bleed through other channels and contaminates your image, make it very difficult to study. So the state of the art is Professor Eric Betzig and Professor Jennifer Lipkotin-Schwartz in 2019. They published a work on Nature. And in this work, through multispectral imaging and following with linear unmixing, they were able to image up to 6 different types of organelles like lipid droplet, ER, lysosome, perox, mitochondria, and Golgi. And this is the merged image in XY and XZ dimensions. So the other challenge for us is when those organelles, most of them share with the same components, which is lipid. So how can we label those different organelles if they have the same components? This is really a challenging thing because when you want to label different organelles, you seek for their different chemical differences. But if they are the same, then they should label the same. So you cannot separate them. So this paradox puzzles us for a long time until we find a solution, which is we don't label different organelles with different colors. We label them homogeneously, and then we separate them. How do we separate them? We use a dye, which is termed now red. It can label the following organelles: mitochondria, Golgi, ER, lysosome, early endosome, late endosome, lipid droplets, TNT, cellular membrane, and the nuclear membrane. And we find that we developed this structured optical sectioning technique, which can reveal the ultrastructure in a very crystally clear manner. So making us being able to study them without any in a very clear manner. And we find that the major components of these membranes were glycerol-phospholipid, spinrolgo-lipid, and cholesterol. And this glycerol-lipid, they were soft and they were floating. And this sphingolipid and the cholesterol, they were very dense. And if you study the Nile red, when in the glycerol environment, it is moving more freely. And in this spheral region, it is limited. So we can use two types of information. One is in a polarized environment. It is red shifted, and in a non-polarized environment, it is blue shifted. And for the mobility, we can study its on whether it's order or disorder through the orientation uniformness from our structured illumination. So by doing that, we have studied a series of subcellular organelles. First, we studied the cell division. We find that, for example, for these two parts of plasma membranes, generally, when your emission ratio drops, your modulation depth increases. So for this PM1 and 2, in different time spots, they were like V shape. And if you go to the modulation depth, it's like an apex shape. And when they separate, they form tunneling nanotubes, which transfers mass from these tunnels. And we find that well, the modulation depth and the emission ratio and the modulation depth, when it decreases, this one certainly increases. However, it's not 100% like so. So, which means when something has been transported through this tunnel, they perform differently. And if you see the modulation for mitochondria, you will find that also this mitochondria is very complicated in terms of both the emission ratio and the modulation depth. And for early endosome, it's more like a plasma membrane because it comes from plasma membrane. However, the performance of a late endosome, no matter the emission ratio or the modulation depth, it's more like a lysosome because its destination is going to form lysosome. And so we have studied the components about mitochondria and the ER Golgi and the plasma membrane. And we found that in general, when your emission ratio increases, your modulation depth decreases. However, there are abnormals like lipid droplets. It has both low emission ratio and low modulation depth. And it has also for the nuclear membrane and ER, its emission ratio is the highest, and it has also relatively high modulation depth, which is maybe arising from the sophisticated lipid interactions. But we were able, through this information, we found that the emission ratio and the modulation depth, they were identical axis, which means we can draw a 2D plot, 2D dot plot for that. And we can better separate them through studying of their modulation depth and the emission ratio. And an ongoing work is by using deep learning, we were trying to separate all these 10 or maybe even more subcellular organelles in different stages or different phases of the cell develops. And this is the spot work. And we are hoping that through this single cell multi-omics capability, we are able to study the organelle interactions and generate organelle interactome, lipidomics, proteomics, and genomics. And more recently, because we were trying to also find more interesting collaborations through this. However, the capacity or the the space and the manpower for my own lab is very limited. So more recently, we have established every instruments a company to commercialize this work, and see some of our results. Wide field, you see SIM in a much larger screen, and for polar SIM, you see a very ultra large big picture, and you can see all the details from the SIM from the polarized SIM result. And in comparing with the previous 1000 by 1000 image, now we extended it to 2000 by 2000, a fourth expansion of the field of view, and we can see more of our specimen. And this work is actually from a series of instrumentation works and software optimization, and also the layout, the size, to reduce the size and make the systems stable. So in the lab, you only do two things: realize the function and optimize the performance. And then you can write up a paper and publish your exciting work. But when I do commercialization, I find that it's not easy. This two step is the beginning. You have to deal with the supply chain, product stability, software reliability, operational fluency, user-friendly, electromagnetic compatibility, miniaturization, user interface, and then we can better address users' demands. And however, what's interesting is when we done that, we find that we can address more interesting questions. So before the end of my talk, I'd like to quote Elon Musk's famous quotes: "Don't just follow the trend." You may heard about first principle. You can boil things down to most fundamental truth, and then you reason up from there. So going back to my talk, my first talk is about the mirror state. So we have arisen from a 4-pi, put a mirror there, and generate a very low cost 4-pi system. And with very limited low power, we can image the nuclear pore complex. We have also imaged the virus filaments of an RNA virus. And then if you go to then we developed this dye, magic dye for mitochondria, and then I starting from the principle of structured illumination, I started to look into the polarization angle, and we developed the polar SIM, and then we expanded it into the spot, the spectral and polarization multi-organelle interactome. So with that, I'd like to thank all the very talented and hardworking students and postdocs in my group, and also previous members. You are great. And also thanks for the constant funding support from the National Natural Science of China and the Ministry of Science and Technology of China and the Beijing Natural Science Foundation. And also, and a little advertising, we are hiring talented postdocs, PhD students, and employees for every instruments. So if you are interested, inspired by my talk and interested in working with us, please send me an email. And that's all for my talk. Thank you.
Okay, great talk. Yeah, Peng, you are really great. Yeah, and
very good time control. Yeah, so it's right on the time. Yeah. Okay, yeah, actually a lot of audience say that I never think about, someone can give a talk for SEM, so fun and so interesting. Yeah, it's fun. Yeah, because like every day they use that instrument and they never know, they can go deeper investment and do a lot of things, discoveries. Even some say, "Oh, okay, I know Xipeng was really good, but I don't know his work was so solid." Yeah, so that's some feedback from the audience. Yeah, we still for the questions I will post out and panel discussions. I will introduce the panel list because today we have a very strong group for the panelists. First is welcome Da Yongjin. Yeah, Professor Da Yong was from University of Technology Xining, and also now he also have a position in South University of Science and Technology. He's in Shenzhen now. Yeah, so Da Yong got his PhD in micro university and also working there for more than 10 years, and now has getting set up a new center in University of Technology and Xining, and he did a lot of nice work, leading work, and most importantly he's a collaborator with Professor Xi Peng. Yeah, they has collaborated a very super breakthrough they get published on Nature, right? Am I right? Natural science, yeah, on Nature. So that's really proud of this, collaborators. Our next panelist is Professor Hong Minghui, our old friends. Professor Hong was delivered talk, I think it's in the end of April. That time was Xiamen University 100 years anniversary. It's Professor Hong's mother university. I got his bachelor degree there, also the master degree, right? And then go to overseas, got a PhD in Singapore, and now he's a superstar there. He's not only a professor, leading professor in photonics, also helped to set up a spin off several companies from his lab, and all his students get to be billionaires or billionaire, right? Professor Hu was a billionaire too. Yeah, so it's very exciting, and share a lot of story with us and his talk, and also he was interviewed by ICANX Stories. I think many people was moved by his story because he, yeah, it's a long way to grow up to be a superstar from the students to be superstar. Also, long way, to help the students to, get the start up to be successful. And now he's, really, really a lot of experience, a rich experience. Professor Hong, welcome. And our challenger today is from University of Technology in Xining, and he's a postdoc from Professor Da Yongjin's group. And yeah, today I already prepared a lot of questions, right? Guo Chen. So yeah, please let's welcome everyone get on the stage. And now we start from challengers. Guo Chen, Dr. Bao, please.
Interesting topic. I have a couple of questions. Now, the resolution can break the diffraction limit. It can reach several tens of the nanometer, right? So what's your opinion on the next milestone for the resolution to achieve? And what are the major challenges or opportunities for us to achieve this?
Yeah, that's a very good question. So for the next stage, I believe it's a wider application of this powerful technology. Super resolution, as you can see, it's an still emerging technology that its full potential is yet to be discovered. And although today I have given several demonstrations of this technology, I believe if you imagine there are a really crowded cell, and their interaction is so rich that we need to study them in a whole new level. That's a quote from the Professor Stephen Hill. He says, "I think every confocal should be studied now." So, so first, I think a wide application of this exciting technologies is certainly one direction. And the second direction is about pushing the limit of the techniques. There are a lot of physical restrictions, but we must be brave. There is no barriers ahead of us, or if there are barriers, we need to find ways to surpass it. So for example, mean flux, it can already reaching a resolution down to 2 to 3 nanometers, which is a new order improvement over the conventional state microscopy. But it is once again, it's a single molecule technique. So the temporal resolution, as I stated, is limited. So we need some other work, maybe to parallelize this work and to make it a very fast yet a very large field of view, and we can collect more information from that.
Thank you.
Okay,
Terrific.
really good. So, Gordon, did you have further questions?
Yes, just the professor, she mentioned the time dimension. So I would like to ask, is it possible to integrate the time dimension to label different organelles for the super resolution microscopy?
I didn't quite catch your question. So
I mean, can you integrate the time dimension lifetime to the super resolution microscopy, right?
I think, yeah, I think that's a very good point. So for the lifetime, as you can see, the lifetime is measuring the time that it jumps from the excited state to the ground state, right? So for STED, we're actually driving using a donut shape to drive it from the upper level to the bottom level. So the excited state, once you have a driving force, it interrogates your lifetime naturally. And we actually, the current physical detection limit for that is a little bit tricky, because we only have several nanoseconds for a conventional fluoroscope. But if you go to upconversion nanoparticles, for example, you will have like 50 microseconds to several hundreds of microseconds lifetime window for you to do that. And I believe that will be a very exciting direction for super resolution. Like I said, a new dimension opens up a new door.
Okay, really good. So now I have a question was from John Hopkins as Dr. Hui. Yeah, I want to ask you. He's doing research in the plant. Yeah.
Plant.
So it's not a living cell like the animal, but it's plant. Is that possible using a super resolution to discover this?
Oh, sure. Thank you for the wonderful question. So although here I demonstrated with the mammalian cells, with animal cells, it's not a limit that this technique can only be applied in animal cell. It actually, plant cell is fully open to that. And as a matter of fact, we are currently collaborating with Professor Jinxin Lin in the Beijing Linye Daxue, which is study of the plants. So once you label your plant cell subcellular organelles with fluorophores, we can handle it. And relatively, it's easier because plants are healthier than the mammalian cells.
Okay, I see. Yeah. That's really good to know that. Also answer questions. Okay, now Dayong, did you have any questions with your calibrator? Dayong, you mute. Yeah. You mute. Yeah. Please.
Yes, I have a very sharp question prepared for the collaborator, but he never know what I'm going to ask. So, if the topic today is talking about developing and exploration of new dimension for super resolution imaging. In optical dimension, we got intensity, we got color, we got polarization, we got time. That's all the dimensions, nearly all the dimensions you already covered. The remaining dimension, the remaining optical dimension will be about the angular momentum, the angular momentum. How do you think we could further use the angular momentum for super resolution imaging as another new dimension?
That's really a very good question that I have never thought before. If you think about STED, it actually has already modulated the light to a vortex. So it's like an first part of the angular momentum in this direction. And I remember there are some works by tuning this spiral vortex face into a different form. It can create a sharper donut, which enables you to generate better resolution. And I believe instantly that if you use angular momentum and optical tweezer together, so if you look at the donut shape, it's one kind of optical tweezer, and the Gaussian is another type. So you can how to say, manipulate your system. You can interrogate with that, and it will create some vibration, and then you were able to image it in a better way. But this certainly has to be. I need an how to say, a more planning to give a more realistic answer to that. But thank you. This is really. It really opens up my thought. I never thought that before.
Okay, that's a new project for collaboration. Yeah, George?
Exactly.
That's a new.
It's a new dimension. Yeah.
Okay. Yeah, Professor Hong. Yeah, please.
Okay, thank you very much. Very impressive talk. You do the great job. Okay, I have 3 questions. Okay, and start from the simple question. The last question may be a long discussion between us. Okay, the first one, I feel very happy you're doing your commercialization. Okay, it's very hard, difficult task. I roughly know the price of the STEP microscope. What is the price tag of your STEP microscope you are aiming to sell?
No, actually, thank you, Professor Hong, for your question. So right now we are actually not commercializing STED, but we are commercializing another technique called the Polarized Theme. So this theme is actually one of first that enables you to dig into the polarization orientation information from the specimen. So it's very inspiring, and in combination with the spectrum, you can study multiple subcellular organelles interactions. So its price, we are trying to lower it, but it's not my role to reveal the final price. I'd like to leave that to
roughly how much? Yeah. 5 million, 10 million.
I think
because your price tag will affect the application of the super resolution microscope. Okay, this is very important.
Right.
Yeah. My second question also very simple. And for the STEP, right, and then the super resolution, how long time you will take to scan one of the image? For example, 10 micron times 10 micron. How long time you will take?
For STED, actually, it's really we can scan the specimen depending on the fragileness or the robustness of the specimen is between 0.5 seconds to 4 to 5 seconds. Yeah. And we can scan it like 20 to 20 by 20. It's an point scanning system. And but for our sim, it's much faster. We can do an 66 by 66 and cover a range of that with an imaging speed of over 20 hertz. So which means it's like 5 milliseconds of exposure time for each frame, because like I explained, we need 9 frames to acquire the whole data set.
So you mean very fast, you can get it one
yeah,
a few
yeah.
second time.
And by using, I forget to mention that actually I have a technology which also I told the idea to Professor Liang Yichen, who is a previous speaker for SIM. So in his Kaizen SIM, if you look into his acknowledgements, you will find that we have this rolling mechanism, which means we can group it one direction, 1, 2, 3, and then another direction, 4, 5, 6, and another direction, 9, 10, 11. And then you can repeatedly regroup by you can accelerate it further 3 times. So in total, you can reach, like right now, we can reach 60 hertz already with a very large field of view.
Okay, so you see it can be very fast. Okay.
Yeah.
The last question, maybe some more of the discussions. Okay. And maybe quite short now. Then the Alex like to have short questions, right? I did not do the fluorescence microscope. The reason here is the sample I deal with is not biosample. Many of our industry sample cannot dot molecule, the fluorescent material. For example, silicon, for the microelectronic chip, right? And then also the metal, you cannot dot, right? Yeah, so now my question is here, same as we do the work. We shine the light beam, we capture the image, we have image. But what is this image? Is it the image we get is what we want? We shine millions of the photon to the sample, right?
Mm-hmm.
And then the light will be scattered back. Yeah, for your case, we have fluorescent back, right? Okay. Then this photon is only show the surface or go into the molecules. How deep we go into, right? Similar case, for my case and your case also have. So my question is, you use the doping, you dop the molecule, dye the molecules. This dye is on the surface of the molecules or go into the molecules. How deep this dye go into the molecules? Similar question. I also have this question.
Tell. Yeah.
Yeah.
Yeah, very good question. So let me explain it in this way. So first of all, is the technique can be easily transferred to like label-free environment? The answer is yes. And the proof is like, I think I didn't give an right now you probably can. Let me tune my screen into none, and then you were able to see. This is the like I explained. This is a grating structured illumination, and this is a transparent specimen. And when I illuminate the specimen with that, guess what? You see moire patterns, and the moire patterns carries the high frequency, and now you can read the characters, right? So without any fluorescence tagging, without any trick, I can already give you an example of how we can do that. And the next one is once I label my specimen with fluorophores, how long is the linker? Is it going into it? Stay with it, or it's like floating randomly. So this is actually it depends on how you label your cell, your subcellular organelle. So the choice of the cell sometimes, for example, like GFP, luckily it inserts into the structure of the organelle, so it's bound very tightly. And actually, as a matter of fact, all the systems that I demonstrated today, it's like we need a tight binding for that. If you don't have that, if you freely moves, then I cannot link their relationship between the direction of the fluorophore and the direction of the organelle. So that's the component one that we need to check. For example, when we use the fluorine to link the actin, it's small molecule linker, so it's very, very close by. But like you're also true, it is also true that if you use an immunofluorescence, then you have antibody antigen, making the system very long, and then you were not able to do this any further. So for my technique, the only restriction is that you need to restrict your dye within your specimen, and ideally tightly binding with each other. If not, like the how to say, the now red, it dissolves into the lipid bilayer, and sometimes it floats, sometimes it's restricted. We can use that information as a new dimension to further separate the environment information.
Okay, thank you
for your
very
question.
much. Thank you.
Okay, very good questions. Actually, our students is asking for Professor Xi. So is that possible for us to send some samples to you for the high, to do some surveys? Yeah. Can you,
Sure. Yes. I have actually I have shown my email information on my very last slide. And if you're interested, please send me emails and we can make connections.
maybe his behind the question is, did you charge?
Yes. We actually right now we are how to say, polishing our instruments to make it really a killer level instrument for the user. So we need at this time being to be slightly selective for the user who is really have challenge questions. So like I said, super resolution is not a free lunch. It's you have to sacrifice something. For example, for STED, you have to use very specific labels, highly photostable. And for a SIM, you are actually, you collect 9 images and then you get 1 sharp image. So we need that kind of user who understand the condition for that and prepare very best specimen with us. So we can help you with that. But please bring challenging questions like all the challengers and the speakers today. So we can have a hot debate.
That's the win the chance, right?
If you just want a free lunch, this is not the place to go.
Okay, I totally agree. Yeah, so I say that the students who are asking for the service, yeah, please at least
Send me
send an
emails.
email, yeah, to Professor Xi, and you should prepare the samples good, and you should prepare some, some charge, some fee for the calibration. Yeah. Okay. Yeah, that's really good. Actually, I have another questions for not from students, from myself. So I know Professor Ming Hui was a spin-off of several company, and then now Peng was a spin-off company too. And I don't know, Dayong, maybe Dayong have more than 10s, right? Yeah. And now it looks like it's a trend for the for the professors, the scientists, try to put more energy to get the commercialization or get the technology, into the market for reality. I think, in this period, what kind of difficulty, the most difficulty you met and you're facing? Yeah. So maybe Minghui, yeah, maybe you can go first because you already have many companies. What's the big challenge, the biggest?
I think the big challenge is, of course, the first we need to have a strong patient. You need to believe yourself, you can success. Okay, yeah, first. The second, you need a very strong team. The team of people who can work together with you, even tomorrow, your company close. Today, we are fight together in the last minute. And then the third one, is your must have good luck. And then, but your product must have the potential, can become product. The product can be sold, can generate profit. These are the most important factors. Thank you.
Okay, very good. So how about Dayong? How many company you have?
I totally agree with Professor Hong and his experience. I think my experience tells me the most important thing is you need to listen to the market. As a scientist, you can do a lot of blue sky research. You can do whatever you want, basically. But if you want to set up a company, you have to listen to the market. What's needed from market. And second is almost similar as Professor Hong suggested. You need a very strong team, and you need to manage the team, and most importantly, manage the milestones and time. Deadlines. So you need to manage the deadlines, time, and projects. So that's being more critical.
Okay, cool. So Paul, yeah. So you are, newcomer in the market, right?
Yeah, I think I still has a lot to learn from Professor Hong and Professor Jin. But certainly, yeah, I have experienced a lot of difficulties. For example, the supply chain. We really didn't realize that some parts they sent to us batch to batch, they were different. So it took us a lot of time. Like Professor Jin has shared, you need to manage the deadlines, but when you have such expectations, your deadlines has to be postponed, which is very headache. Yeah. So, but throughout all these efforts, you really find that in the beginning, when you do scientific research, you have a lot of open source resources, and you can tune the system so that it might work now and then, and in the middle is the time you tune the system. But when talking about a product, it has to be perfect. You have to link all these dots by yourself, and you have to make it so stable that once the user turns the key, it works. And it works really every day like that. So a lot of work has to be done, but it's really worthwhile experience. It's new to me, but really worthwhile.
Okay, yeah, that's really cool. So now we have the last chance to our challengers. Guo Chen, did you have any questions to ask us three supervisors?
I would like to ask Professor Xi, since the luminescent probes are always needed for the super resolution microscopy, so from a material standpoint, what is the ideal probe for the super resolution microscopy? Or in other words, what can material scientists contribute to this field?
This is a very good question. So I always share this observation that if you think about the Nobel Prize for super resolution, it's a physical breakthrough. It's definitely applied in biology, but it is awarded the Nobel Prize in chemistry. So it means that this cross-disciplinary study, it's not originated from any single field. It's a joint effort from all the disciplines. And in terms of for the material scientists, I can quote, I can refer you to the successful story of Stephen Hell. You see that he has also established a very successful company called Aberia. But if you go to Aberia's website, you will find that it's a picture of two walls of their company. Left-hand side, orange, stands for Aberia Instruments. Right-hand side, in green, painted in green, it stands for the Aberia dies. So you have to make the dies fit for the specific questions so that you can fully demonstrate the full power for your instrument. And different techniques has different requirements for that. For example, single molecule, you need to make it blink very fast, and instead you need to make it photostable, never blink. So you need to first ask which instrument or which technique am I working for, and then you can tune the features for the material, for the dies to better address those questions. But thank you for the wonderful question.
Okay, really good. Time flies. I thank you all of you. Actually, the last question I want to get everyone comments on this, because one of the audience from I don't know where, he said that all are Chinese there. Why you not speak Mandarin? Why you speak English? Because I say we have something must to say here. ICANX is a platform for international. It's a platform for the professional, communication and to share the technology and the science worldwide. It's not just shared inside Chinese. So though all the Chinese professors here, students here, we have to be understanding. We have to be more international and professional. I think this, maybe Professor Hong, you can add in some words here. Why the students have to, get through their English? Yeah, Professor Hong, did you have any words?
Okay, I think so. I agree with you. The English is international language, and then we have so extensive the research in the world. Not only just we are the Chinese background researchers, and then we also need to communication with other people. Research is not the country base. It's the communication. It's the sharing. It's publicity. It's the communication, and then we join our research work together. So we need to go to internationalized. Yeah.
Exactly. Yeah, Dayo. Yeah, I like you first.
If we decide use English as the common language to communicate science, we should stick to the English and for the type of communication. We publish paper in English. We have holding international conference in English. And here, although we come from the Chinese background, but doesn't mean, we could, give up the English as a more important communication channel. So again, research doesn't have the boundary, and we need more impact to be delivered and reaching to the very small corner of the world.
Okay, very good. I think, Paul, you have a good experience, because now you get, you're from the white powder now to be so, smooth and friendly in English. Now you get famous in the world. You can, say something to the students.
Yeah, I think for first of all, actually yesterday I have delivered an interview in Chinese. If you would like to hear some of my story, it's quite informal interview. You can also go to the ICANX website and listen to my story, which is interviewed yesterday. And speaking of the language, I think language is a tool for us to communicate with different people. So if you go to the Bible, there is a famous story that in the beginning, actually, all the nations, they speak the same language. And soon they want to build a tower to go to God, which means, and God feel the threat. And he says, let's change their language, make each nation speak one language so they cannot communicate. And by doing that, it breaks the people's communication. So from this story, you can see that language is a tool for us to link to each other. In the screen, you see 5 Chinese faces, but behind this screen, do you know how many people they are looking at our interviews and they can enjoy? And imagine if we only speak Chinese, how limited that number would be. And it's a pity that the English-speaking people cannot enjoy my talk and my science today. So being the fact that we need to choose one language to communicate, right? We cannot speak 2 different languages simultaneously if you don't understand that. And being the fact that English is still the dominant language in the science community, here we choose English to communicate. But I'd like to share that language should not be a barrier to limit us. Let's surpass that barrier.
Okay, thank you very much. Thanks for saying this. Actually, I want to conclude here is, how many people's working, IKX talks. That's from 5 continental, more than, 20, 30, or 50 countries in different areas, in different place. And most of them get online every Friday. No matter is in the morning, in the afternoon, or in the evening. So a lot of people here, they want to share the story, share the technology, share the science. So that's why we choose English as a language. We try to, build up such a good communication platform. We hope our Chinese, our best, our latest results can be known by the whole world. Also, we can know the whole world what's going on. So that's why, we stay here. We keep on going. For today is 70 weeks. 70 weeks. More than 1.5 years we stay here. So if you like to get communicated with the whole world, please join us. Okay, thank you all of you.
Thank you, Alice.
Paul, here
Thank you all.
I have a special certification for you as our normally I can access talks. So you deliver a very nice talk, silver resolution, adventure. I like that word. It's a really adventure for all of us. I think you deserve this certification. I will give to you when we meet next time. Okay, thank you, Peng.
Great, thank you so much.
Okay, so as I said at the very beginning, now I repeat again to announce this. IKX welcome all the young scientists
to join us. We got this Young Scientist Awards. Now it's calling for nomination and self-nomination too. And all the people who got PhD, and vision 10 years, you are, have independent works, achievements, you are welcome to submit, your material nominations to us. We will do the selections and evaluations worldwide. We will give all these, awards. We have the committee as very internationally, not only from China, myself, and also my colleague Paul Weiss from US, and Fu Lan was from Australia, and Yuri was from the east coast of US, and Jürgen Brugger was from Europe, and we also have two young scientists at demonstration, Miso Kim from Korea, and Martin So was originally from Kenya, and now he's a professor in Ahoa. So the prize, who wins the Young Scientist Award will get $500, and also we get the chance to deliver a talk at ICANX next year. And thanks to all sponsors. And in the end of this year, we will get the people go together to have ICANX Summit. We will go to Hainan, the best island in mainland China, and welcome you to join us, have more fun, to meet the speakers face to face, to have more discussions, and to get more collaborations. And next week is October 1st, our national holiday, our national day. So we will have the beautiful, female scientist, Professor Lin Yuan, to get on the stage. And she is from University of Electronic Science and Technology of China in Chengdu, and we will have great people together to support this talk, flexible inorganic thin film devices for the bioelectronics. Welcome to join us next week, next Friday. See you at ICANX. Okay, bye bye. Thank you.